Okay, hello everyone to today's seminar. Today's seminar will be given by Sergey Kumkov from Ekaterinburg in Russia. And I think he's a very well-known scientist in the area of interval methods. And yes, maybe a short biography. Sergey graduated from the Ural Federal University in 1964. And I think since then he has been very active in many areas. And one of those areas in which he's currently working is the processing of noise data, also dealing with some outliers. And in today's presentation, he will show us how to use interval methods for that purpose.
Yes.
Please, Sergey, we're looking forward to your talk.
Yes, my talk will, dear comrades, my talk will be devoted to this item. You see the title of it. Further, and the aim of this presentation is to demonstrate a survey of tried applications, namely tried in practice application of interval analysis method. And the problem which will be discussed is processing the noise data with two-dimensional uncertainty from several information sources. These are usual slide, motivation, noise, problem, and formulation and processing procedures. And motivation of this research is that the standard documents, very strict and official documents, GOST, the state standard, and the state recommendations demand for processing to be validated a representative sample of measurement, at least 15 ones, and known probabilistic characteristics of the error measurements. But in practice of the air traffic control, typical situation when the sample are very short, 1, 2, 3, or not more than 4 measurements from the current instant of the aircraft position. Then the probabilistic characteristic of the errors in measurements are unknown. And the most important remark is that the standard statistical methods do not take into account the sophisticated the so-called, uncertainty set of each measurement. It's very important. So we use standard interval ideology of processing data with the uncertainties. For example, in the marvelous Sergey Petrovich book, and from the book of Ural. It's very interesting. Then, as the main procedure in our constructions is the intersection of the uncertainty sets of the measurements with some auxiliary sets of aircraft positions. For example, we can see on this slide what measurements come from the measuring systems. The bank system, then GPS system, observing radar system, and from the onboard navigation system. Here I show the cases when the current measurements are closing. That's the uncertainty sets contain the true aircraft position. It's very important because our further steps depend on do these uncertainty sets intersect or not, or partially intersect, for example. So we formulate the problem, having the measurements with the uncertainty sets to improve the set of current aircraft position, compatible with the given situations. In two situations, when all the measurements are closing, or when measurements are not closing partially or completely. And the main procedure is intersection, as I told, of these uncertainty sets and with some additional auxiliary sets. Usually, I must say that usually in practice, engineers and aircraft ATC operators construct the rough auxiliary set of predicted possible positions. And those measurements which lie out of this set are called outliers and do not participate in further processings. But in the case, most pleasant, by the way, when all uncertainty sets of measurements intersects, we obtain the informational set non-empty. Thus, the information set exists. And in the insertion, I show that that case. And in this case, the intersection of all these uncertainty sets contains both the circle, the true position, and as the output estimate, we give out, for example, the central point of this set, because we do not know any probabilistic characteristics, you see. And delta X and delta Z could be the estimates of accuracy of this output estimation. But we often meet the situation when some measurements are not closing. For example, on this slide, I show that the measurement, this green measurement from a radar system is not closing. But nevertheless, intersection is not empty. This informational set is not empty. And know that such intersection is most close to the true position. It is very interesting fact that we discovered. So if intersection is not empty, we can continue to use the information set as the information for giving the output estimates. But what to do when all the measurements are not closing? Here we see that all 4 measurements from 4 systems have the uncertainty sets which do not intersect. What to do in this case? In practice, engineer immediately suggests the following: let us construct or build the outer box which contains all these uncertainty sets, and as an output estimation of the aircraft position, let us give out the central point of this envelope. This is very often used in practice, I underline. But this procedure can be enhanced or sophisticated. Namely, let us construct the minimal outer envelope, convex envelope, of course, of these uncertainty sets, and let us give out as an estimate its central point. In this procedure, the gray parts do not participate in further construction of the central point, and its value is more accurate, as the simulation and practical measurements show. But this procedure can be sophisticated, namely how to give out the central point. Let us reconstruct the envelope of these uncertainty sets. And note, under this, we do not lose any information about measurements, both the measurements and their uncertainty sets. And let us ascribe the circle with max-min radius and give out as an aircraft position the center of these circles. Very often we meet the situation when it's possible to ascribe many circles with such property. And in this case, the central point may compose an interval. And as an output estimation of aircraft position, we can give out this point, namely the black square. But more fine dynamic filtration can be used. See, for example, Kostousova work. It is very advanced. Our investigation researcher in the institute, which works with dynamic systems. What it is doing by this approach? Namely, the first auxiliary sets are formed by intersection of the uncertainty sets with the fine, accurate predicted set of possible position or aircraft. Namely, this we have the previous information set at the instant tn minus 1, and we predict it to the current in instant tn and intersect with it. After that, we apply very useful construction of the convex envelopes of the uncertainty set parts inside the G predicted. And again, ascribed in the envelope these special circles, obtain interval of possible positions, and give out at an aircraft position the central point of this interval. This is shortly the procedures we have probated on the interval measurements and the interval simulation. And so we can make the following conclusions. Implementation and simulations of the elaborated approach to processing noise information. So have shown, for example, we describe it in this work and then this work, that application of the interval analysis allows us to use constructively information of the measurements uncertainty sets from each of various information sources. Know that this information is not taken into account in the standard statistical methods. Further, our approach allows us to obtain, in the cases of all closing measurements, the accurate set that with guarantee contains the true aircraft position. And in the cases when some measurements are not closing, but the information set is not empty, we found that the set is placed most closely to the true point. It's very, very pleasant fact. And the last conclusion is that in the cases when all the measurements in the sample are not closing, The interval approaches give more validated estimates since using additional information of the measurement results and forecasting of positions of the dynamical system. That's all, dear friends. Further, there are references. Thanks for your attention.
Okay, many thanks, Sergey, for your very inspiring presentation. And I think your talk is now open for discussion. And who wants to start with the first questions?
Yes, I'm ready for constructive critics.
You can start.
For constructive critics.
Question. The first question.
Yes.
Sergey Ivanovich, we jointly prepared an interesting methodological article on the issues that you told us today. And in this article, written in Russian, of course, we discussed possible English terminology of some concepts you used here in your talk. And so I'm very, very surprised that you talk about closing measurements. Actually, we use the term enclosing measurements. Do you understand the difference? Not closing, enclosing.
Overlapping, yes.
Enclosure, or alternative term is covering measurements. So covering or enclosing, not closing, because the sense is totally different. Yes.
Thanks. Yes, I'm sure they agree with you, and of course, maybe more appropriate term could be overlapping or reclosing. Yes.
Sergey Ivanovich.
Yeah.
I see your presentation, slide 8, and the text somewhere in the third or fourth line of within the slide 8. The cases are shown where the measurement at the current instant are closing, that is, their uncertainty set contain the true aircraft position. This is exactly enclosing measurements or covering measurements, not closing.
Reclosing, yes.
Not reclosing. Sergey Ivanovich, I can provide you with a link to our joint paper at all relief. Look at it attentively. Carefully.
Yes.
Enclosing is a better term.
Yes. Thanks for your remark. Further questions, please, if possible.
Yes, I think Luc is the next one who wants to ask something.
Yeah. Thank you, Sergey, for your talk. I have some question about outliers. If you want a guaranteed method or to enclose the true solution, do you assume something on the outliers? For instance, do you assume that you have a maximum number of outliers, or do you have any assumption that make you possible to guarantee something, even in the case where you have this kind of outliers?
Mm-hmm. Yes, if all measurements are reclosing, I correct myself, then this intersection is not empty. Surely, and that is with guarantee contains the true position. Correct. Do I answer your question?
Yeah, yes, but sometimes you have outliers, and but you can assume, for instance, that you have at maximum 2 outliers, and in this case, you can still guarantee you can enclose the true solution. But here, since you consider a situation where you have outliers, do you have any assumption that make you possible to guarantee something?
Yes, of course, but I can say that usually we trust the measurement systems, and that's one we hope to obtain the non-empty intersection of these measurements, of these sets. Of course, the case may be when all these measurements, and their uncertainty sets give after intersection the non-empty information set, but being shifted somewhere from the true position, surely. But it's necessary to trust anybody, for God, for the measurement system, etc. Surely. So that's why I say that if usually the systems give reclosing measurements, and we obtain such example. But if some of measurements is non-reclosing, we can obtain this intersection, but we have found that in such cases the position from this information set is most close to the true position of the aircraft. It's very interesting detail.
But for instance, if you have an empty intersection, you can assume that maybe you have surely at least one outlier. And then from this, you can also, like here, for instance, you may, in this situation, you are sure that you have at least one outlier because they do not intersect. So maybe if you make the assumption that you have, let's say here, 2 outliers at least, then maybe you can guarantee that you are in the intersection of the set taken by pair. Okay, so thank you. I think I have understood.
Well, thank you for your remark, because you see, if we trust to GPS, for example, or internal onboard navigation system, it's very useful. And usually GPS gives with very accurate, with high accuracy. For example, for the aircrafts, we have accuracy about 20 or 30 meters, and usually these two uncertainty sets intersects and give a non-empty intersection. You see?
Yes.
But in comparison with the observing radar system, this uncertainty set is can be very large. For example, 1 kilometer or 2 kilometers even. The bank systems gives accuracy about 100, 200 meters. And usually, if it possesses the true position will be an intersection of these, for example, 3 uncertainty sets.
Okay, maybe let me add something to this discussion that you just had with Luc. You assumed, or at least Luc assumed in his question, that he knows there may be some outlier for sensors that were correctly calibrated. Now, let's play a little bit around with this question further. What would be happening, for example, if you want to calibrate your sensors using the data? Did you handle such topics in your work, or what are your suggestions?
Yes, of course. before accepting the measurements from the uncertainty from the measuring systems, we asked the corresponding technicians have the system is calibrated or not. You see, that's why we trust to the measurements.
Okay, that means the calibration task was something already performed in advance, providing some guarantees, and on top of this, you're performing, yes, the complete work of signal processing, and you're discussing the issue: are these different measurements enclosing a common set or not?
Yes, I can say that usually in the beginning of every duty of each system, the technicians perform the calibration of every system. You see, and that's why we can trust to the measurements.
Okay. In fact, I have a second question. Maybe you could open the slide number 21.
21, just a minute.
Yep.
Just a minute. 20, 21. This one, yes?
Yes, this one. Where you had your output point, this black square in the middle of your box. You have several kinds of different information sources there with which you're trying to estimate the true position, or let's say your output point. Did you consider also something like, let's say, some weighted superposition? For example, something not really in the middle of the resulting rectangle, or would you recommend always to deal with a box and the center point of the box is the corresponding output?
Usually, if the onboard navigation system works without interruptions or strong disturbances, we can trust to this predicted sets G, because its sizes depends on the time of predictions. But time of prediction is usually 1 to 5 seconds, you see, and with this, and under this, this set, predicted set, contains the true position, the true points. That's what we try to do, to apply the dynamic filtration as Kostausova made, for example. But I can say that it can be, the predicted set could be not as a parallelogram, parallelepiped, but can be of some curve form. But it can be approximated by polytope, for example. You see, and the intersection can be successfully performed.
Okay, many thanks. Do we have any further question?
Hello, Andrea.
Yes, Stefan, please.
I have one, if we have time. Thank you, Professor Kumkov, for this nice talk. I have one question about the work. You mentioned the work performed by, I guess, your colleague, Professor Valery Patsko. And I guess in the reference, in the bibliography, you have one article written, you mentioned one article written by Professor Valery Patsko. And
Yes.
I would like to know, I will be pleased to know, how do you want to merge, to mix together what you present today and the work performed by Professor Valery Patsko, and if I am right, I guess the work performed by Professor Valery Patsko is more related to collision avoidance, interception, differential games, I guess.
Yes, I can say that we work together with Professor Valery Patsko and the corporation with which we collaborate often use the predicted set G predict for analyzation of dangerous clothing or even you see, or even in other dangerous cases. And in the work which you mentioned, we described how we discuss how we create prediction of the predicted set in three-dimensional, 2 and 3-dimensional space. You see?
Okay, thank you very much. And to go further, I guess Professor Valery Patsko worked with another Sergey Kumkov. I believe
Yes.
this other Sergey Kumkov is your son, but maybe
Yes,
I am wrong.
yes.
Yes, huh?
Yes, Sergey Sergeyevich.
Yes,
Kumkov.
Sergey 2 times with
Yes,
middle
2
names
times.
Sergey. Huh?
Yes.
Yeah,
But they
yes.
are concentrated on the dynamical systems and the dynamical games for the problems you mentioned. You see?
Yes, you're right. Thank you. Say hello to Sergey because your son, because I know him, your son. Huh? Okay.
Yeah.
And by the way, I know that Sergey, your son, has very interesting tools to draw intervals, box in 3Ds and so on. And it could be interesting to reuse this type of tools to draw the box and the intervals with noise, measurement, noise
Yes.
you present.
Yes, so polytopes, for example.
Yes.
Yes.
Polytopes, yes.
Thanks for the question. I will pass your greetings to Sergey Sergeyevich.
Thank you very much.
Okay.
Then Andreas.
Yes, do we have any further questions?
Maybe I have a question. Outliers happen every day. How do you know which point is outlier?
Sorry, can you repeat the question?
How do you know which measurement is outlier?
Yes, I told that in the engineering practice, they use approximate box, for example, and very often we have the following picture, namely the measurements which lie out of the rough predicted set are called the outliers, determined as outliers. But as for us, we use not only the measurements, but use their uncertainty sets. You see, Marek? And that gives us, this gives us additional information in these cases, for example. And in these cases, for example, when we use the uncertainty sets of which measurement. Because you see, if we intersect it with convex envelope or with the predicted set in this figure, in this slide, we use this part, you see, and this part of uncertainty sets, and that we hope that if the true position is in these spots, they will use and will be enclosed in the output. output set. That's my answer.
So the method is more intuitional rather than well based in probability or interval math or other mathematical grounds.
Yes. If we could have the probabilities of distribution of each measurement on its uncertainty set, then we could prescribe the probability of placing the true position in this set, or in this part, or in this part, for example. But now, as you noted, we rely on our intuition only.
All right, thank you.
Do we have any further questions? Okay, if this is not the case, I think it's time to thank our speaker again. In the meantime, I've also received the PDF file of the document mentioned by Sergey Petrovich. I'll put it also on the webpage that, yes, we get the corresponding link to the question in our today's seminar. And yes, thanks again for the presentation. Thanks again to the audience for asking the questions. Thank you, Sergey, for answering. And yes, I think it's time now to close today's seminar. And yes, see you again on Friday in 2 weeks. And on the 9th of April, we have the next talk in our seminar on interval methods to control engineering. Okay, have a nice Friday afternoon, evening, and nice weekend.